Bachawadi, good morning and good evening, whatever is applicable to your time zone. We are going to start with this chapter in class 9 CBSE as per the new NCRT syllabus, which is about exploring science. So we are going to touch base on many topics on this particular chapter. One is basically how do we explore science? How is a curiosity generated? How do we answer certain questions? How do we explain certain natural phenomena? What are the basic streams of science, for example, physics, chemistry, mathematics, or maybe biology? And what are the things that we discuss on these? And there are also certain aspects that we are going to touch base on. For example, if let's say there is a superstitious belief as to during the times of when we say eclipses, we do not follow certain customs. So these are things that we are going to study. Also, we are going to check based on SI units, standard international units, and what are the confusions that are caused if we don't explore the system of standard international units. For example, there is an instance taken wherein, in this book itself, wherein the plane was flying and because it had not calculated its journey in terms of standard units of kilometers, it ran short of fuel. So these are things or rather mishaps that might happen if we don't follow science or have a rational approach. So in this particular chapter, which is a starting or rather chapter 1 of your new NCRT syllabus, we are going to explore what is the scientific world. So let's start up, guys. Okay. So here we have what is science. So science is not just a collection of facts. It is not just a collection of facts. It is a way of knowing things. Okay. It tells us how we know what we know. So what was the process that was considered before we are knowing what we are supposed to know? So it's a collection of facts. Definitely it's a collection of facts and it's also a way of knowing things. Science starts with wonder. So obviously, the sky which is filled up of stars, it's a wonderful thing. And there's a certain age to which we will basically consider this wonder. After that, we try to explore science in its facts and figures. Some natural phenomena which is constantly occurring, which leads us to a wonder experience, and then we conduct very careful experiments. As you enter secondary stage, so we are entering the secondary stage, which means 9th, 10th, 11th, 12th, and so on and so forth. The focus shifts to deep exploration. So when we were kids, we have learned Twinkle Twinkle Little Star. So that's something wonderful phenomenon that is happening in the atmosphere. So this wonder basically changes into careful experiments, and on the basis of the deductions from these experiments, we move on to the secondary stage, wherein the focus shifts to deep exploration. Okay, asking better questions, which is a very important aspect of science. So the questions that you are going to ask, or the answers that you're going to seek, have to be very rational, thinking more carefully, and understanding how scientific ideas help us make sense of nature as well as technology. So all this has to be blended and first started with a very rational approach. Now, scientific models, the natural world obviously is very complex. We have a lot of phenomena happening. Some are disastrous, some are eventually helpful. To study this, scientists use models, simplified versions of real things that focus only on what matters for a particular question. So we have to downsize. There are so many concepts in science. We have some concepts correlated to physics. We have some concepts which can be only explained by chemistry, and we have concepts which can only be understood in terms of biology. What scientists are doing is they are downsizing things. They are actually correlating it to one aspect only. We cannot take into consideration all the aspects at the same time. Making a model means deliberately ignoring some details. So at times we have to ignore certain details. For example, in higher classes of physics, you will mostly encounter many derivations in which it is clearly mentioned negligible lower quantities, or negligible, we are neglecting the lower quantities which might occur in the experimentations. Okay, so we have to neglect some details. Some things are in such a manner that we have to actually consider the crisp form of it. This is not a mistake, it is done on purpose to keep things simple enough to study. So there are some major aspects which we cannot ignore. However, during experiments or during our observations or during our conclusions, we tend to ignore, and this is done deliberately so that we get a correct picture or we get to know the detailed study of a particular function. Okay. So is science just a collection of facts? Yes, definitely it is. It is definitely a collection of facts. Science is also a way of knowing things. As you enter secondary science, the focus shifts from simply noticing nature to asking better questions and thinking carefully about how we know what we know. So how did we come to know what we actually know? For example, if I say that the weight of a person is m into g, where is this coming from? Or how do we know that the acceleration due to gravity is influencing the weight of a person? So how do we know this? Okay, okay, let's move on. So let's say we have three dimensions, or rather, three major dimensions of science. So one is physics, a moving car. So let's say we are talking about a moving car. A moving car is treated. What is ignored? So when we are talking about a moving car, okay, we are ignoring its shape, we are ignoring its color, we are ignoring its size when we are studying this in physics. So this moving car can be represented by just a dot. It's a moving body. Okay, so we are moving. So I was just trying to discuss as to what we tend to ignore. So there is no there is no co-reference to the shape, because all of them will be obviously governed by Newton's laws irrespective of the shape. Then we tend to ignore its color, then we tend to ignore its size as well. So these are things that while studying the movement of a car, we tend to ignore. When we are studying chemistry, atoms shown as spheres. So atoms are shown as spheres with electrons revolving around them. And what is ignored is the quantum part of it, which is higher dimensions. Okay. Higher dimensions show that the atoms or the other electrons are revolving in waves, and we cannot have a certain defined position of an electron. However, when we study for feasibility, we assume that the electrons are moving in spherical orbits around the atoms. Okay. Biology, cells are shown as labeled. Individual cells are different. For example, the same cell is different in a plant and in an animal, or different formats of animals as well. Earth is treated as smooth, but Earth is not smooth. Earth has got mountains, it has got valleys, it has got rivers and whatnot. Okay, so these are certain things which we ignore. Okay, for example, when we have in physics a moving car, it's a moving car is a single point. We can represent it by a single point. So this is a dot with which we can represent it. So what we are ignoring is the shape of the car, the size of the car, the color of the car, aspects which are not extensively discussed in physics. For example, we have a model of an atom. This is the model of an atom. Atoms are spheres with bonds. So these are spheres. What we are ignoring is the complex quantum behavior of an atom. Okay. Then we have in biology, this is basically a cell. Cells are labeled as diagrams, individual molecular movements. This is something that we are ignoring. Okay. For example, Earth. Okay, we have Earth as a smooth layered sphere, but inside the Earth, or even on the surface of the Earth, we have mountains, valleys, ocean depths, etc. Okay, so as models become more complex, we add more details back in for greater accuracy. Okay, so there are certain things which we tend to ignore. For example, when we are talking about a cricket shot, a person or a batsman undergoing a cricket shot, if you want to predict whether a ball will cross the boundary for a six, you will need the mass of the ball, speed, direction of hit. You can ignore the color of the ball, brand of the bat, and amount of grass on the field. So there are certain things which you can ignore when you're talking about, or whether when as a batsman you are making a calculation that this is the speed of the ball and I need to hit a six which has to cross the boundary. I can ignore the color of the ball. I can ignore the brand of the bat. I can ignore the amount of grass that is on the field. Although these factors are also in a way important. Okay, but we tend to ignore them in a context in which we are trying to study. Okay. As models become more complex, we add more details for greater accuracy. For example, we have a scientist whose name is Meghanand Shah, was a great Indian physicist. While studying light from stars, he did not try to model every atom or every reaction. Instead, he treated the is a star, matter in a star is a hot gas. So he said that the matter which is there in a star is basically a hot gas. He ignored all the complex processes. There is a lot of complexity with which a star is formed. For example, there are two stars which are coming in between. The air in between them gets compressed, or rather, the atmosphere. There is no air, but the space in between them gets compressed, and so on and so forth. He ignored very complex processes, focused only on temperature, pressure, and how atoms form ions. So within a star, how how much is the temperature or how much is the pressure, and how at high pressures the gases that are evolved in forming the stars eventually become ions. Okay, this simple model helped him explain why the color of a star is connected to its temperature. This is a great example of how ignoring details can lead to powerful discoveries. Now, what he was trying to study is the color of the stars. So, he directly correlated it to the formation or rather temperature of the star. So, because of the temperature, there is a certain pressure that is created, and because of the pressure, the gases that are there actually form ions, and that imparts the color. So he is not trying to go deep into the formation of stars. The context of the study might compel you in science to ignore certain details which are not required, but at the same time, uh, it's not a fact that these details are not there. These details do exist. However, in the context of a particular topic of a study, we tend to ignore them. Not everything can be explained. Everything can be explained again, but not in the context that we are trying to study. So we need to filter out information. We need to filter out information. It's like making tea. When you are brewing tea, you actually filter out the tea leaves. So in the same way, when you are studying science, at times based on certain topics of certain chapters of certain streams of science, you have to ignore things. Okay. So the art of simplification, the natural world is too complex. Obviously, there, I'm sorry, there are a lot of phenomena that are constantly happening. Scientists use models, simplified versions of real things. Making a model means deliberately ignoring some details. This is not definitely a mistake. It is done with purpose. So ignoring things is done with a purpose. So mass of the ball, what we keep is mass of the ball, and what we ignore is the color of the ball. What we keep is the speed, what we ignore is the brand of the ball, direction of it, amount of gases on field, amount of grass on field. So when we are just talking about a cricket shot, a batsman is playing a shot, the intention is that he should hit a boundary, or maybe it should cross the boundary. In whatever ways, the calculations are what is the mass of the ball, the speed, and the direction of the hit. So that will be determining the entire motion of the ball. But are there other factors which are correlated to this motion? Yes, they are, but they are negligible. Okay, color of the ball doesn't actually matter. Okay, brand of the bat, you have different bats these days. What is the power? What is the size? Amount of the grass that is there on the field. All these factors do matter. But in this case, on a broader perspective, these are the only factors that we are going to consider for the explanation of motion of a ball which is hit by a cricketer. Okay, let's move on to the other one. Complex realities. So there is a simplified model. There are so many things entangled up in science. Okay, we need to filter out things in order to have a clarity on the different topics. Okay, treated star matter as hot gas. So Meghanand Shah, what he did, so the simple model successfully explained. I'm sorry. Meghanand Shah was an eminent scientist of India. This simple model successfully explained why a star color is connected to its temperature. Ignoring details led to powerful discoveries. So ignoring details eventually led to powerful discoveries. He said that there is a certain temperature in the star because of which the pressure of the gases which have formed the star gets influenced, and because of this ions are formed, and this imparts color to the star. Okay, the star is unfairly used as pressure co- co-temperature, the gradients that on the temperature, focused only on the temperature, pressure, and ion formation. The sonated of the temperature, pressure, or gradients of temperature and chemical formation deliberately ignore complex atomic processes. So in this study, there were other things as well which were ignored by him in order to have a clarity on how the color is imparted to stars. Deliberately ignored the atomic complex gases or bring the identification of at atomic levels, there are a lot of things that are happening in the formation of a star, but he deliberately ignored it in order to understand how the color is imparted to stars. Okay, so what when we talk about what it means in science, let's say when we are talking about a law, it describes a regular pattern in nature, often written as a mathematical equation. Example, Newton's law of motion. In Newton's law of motion, you have something called as ma. So this is a law. Okay, this is a law. Force is equal to mass into acceleration. This becomes a law. Explains. Now, what is theory? Theory is explaining why a pattern occurs based on evidence collected over time. Example, atomic theory. Now, in the study of atomic theory, you see there were many scientists who did many things. Okay, so many contributions were made from different scientists in the study of atomic theory. A broad idea that applies in a given situation. Example, conservation of energy. A shorthand for a quantity. Example, mass, velocity, force, current. So there is a shorthand principle or symbol that is applied. So the language of science uses words very carefully. Many words we use in daily life have a specific and precise meaning in science. Science also uses mathematics, so there is a contribution, or rather a very big contribution of mathematics as well. We know a very few scientists who were not influenced or who were not impacted by mathematics. Okay, so this has to be there. Equations are not just calculation tools, they are complete statements that describe how things are related. For example, knowing the distance, time, and velocity of an object allows us to predict where it will be at a later moment. You have different equations of motion which you are going to study. Specific predictions. One of the greatest strengths of science is its ability to make predictions. How to predict? Telling us what will happen before we even do an experiment. Example, using motion laws, predict how a kicked football will travel. Using chemistry, estimate how much carbon dioxide a reaction will produce. Using biology, predict how breathing changes when you run. So when we are basically motion laws, which is basically a part of physics, we can predict, or rather, say how the ball will travel when we are kicking on that ball, or whether a player is kicking on the ball. Using chemistry, we can also say how much of a particular gas is evolved. Let's say in this case, it's carbon dioxide. And using biology, we can also predict the breathing changes. All of a sudden, there is a requirement of oxygen by your body because your body needs energy. So there is a high amount of respiration that is involved. So that is also explained in terms of biology. Predictions are not guesses. These are not guesses. They are reasoned expectations based on evidence and careful thinking. So these are expectations that are based on careful thinking. When predictions match observations, confidence in the science grows. When predictions do not match, scientists go back and re-examine their models, assumptions, and measurements. So checking a prediction, Varsha tells Meghna, it will rain this afternoon because the clouds look dark. So the law is what? Describes a regular pattern in nature, often an equation, Newton's law of motion. So the theory is explains why a pattern occurs based on evidence. So there is an atomic theory principle, a broad idea applying to a given situation, conservation of energy, symbol, a shorthand for a quality, speed of light from Latin cetas. Okay, so there is basically a law which describes a regular pattern that is often observed in nature. For example, we have Newton's laws of motion. Okay, so law is basically describing a regular pattern in nature, often an equation. For example, Newton's laws of motion. Okay, explain why a pattern occurred based on evidence. So we consider evidences and a broad idea applying to a given situation. Example, conservation of energy. Now we use certain symbols. For example, for momentum we use P, for force we use F, for initial or final velocity we use U and V, T time, current I, and so on and so forth in order to shorten things. Maths is a language too. Equations are compact statements describing how things are related. For example, if I say S is ut plus half at square, in this case, I will say this is displacement, this is initial velocity, this is time, this is acceleration, and this is time. Okay, so these are things that are there. It will rain this afternoon because the clouds look dark. So let's say by using certain aspirations or rather certain things that we have in mind, we can say that it will rain in the dark because it has become dark. So that's a scientific assumption that we are making. Okay. Okay. So checking a prediction. How do we check a particular prediction? Varsha tells Meghna it will rain this afternoon because the clouds look dark. Now, there is a prediction that has been made based on human experience. Is there science involved in this? Yes, there is. But at times, it might not rain. Okay. To make this a proper scientific prediction, Meghna should ask measurable questions like was the sky condition, what was the sky condition the last time it rained? So the last time it rained, we had seen the sky condition as filled with clouds which are dark. There is no sun to be seen, and there is an environment of high humidity. Okay, what's the humidity level? So these were things that we had noticed the last time it rained. What is the wind speed and direction? So how is the wind blowing, or what is the direction? At times you have rain laden clouds above you, but due to the high speed of winds, they are moved from one place to another, because of which, in spite of having rain laden clouds above us, we might not experience rains. Okay, is the temperature dropping like it did before the recent rains? So temperature drops, obviously you have a hot sun which automatically goes off. This hot sun vanishes and it is taken over by rains. Okay, so these are some normal questions that anyone might ask. Okay, and this is on the basis of the observations that we have made in the previous phenomena of rain. We are able to predict that it will rain or not. Okay. These questions go beyond opinion and look for measurable pattern based evidence. So these are not opinions. I am saying that I feel that it rains. No, it's not a feeling that you have. You have certain experiences that you have gathered, and that's a very scientific approach. When a person who is not maybe educated, or who has not been to a college, or who has not studied science at all, but he can say by just looking at the sky whether there is a probability of a rain or not, because the previous experiences have added up. So what are these experiences which are measurable? How much of rain clouds do we see? How much of dark clouds do we see? How much has the temperature dropped? Are we feeling the humidity? So these are experiences based on which he makes a prediction. But definitely there is a science which is involved. Okay. Why do weather forecasters sometimes go wrong? Weather depends on temperature. Obviously, weather will depend on temperature. It depends, yes, on pressure, humidity, and wind. All constantly changing. These factors are constantly changing. Okay. Tiny differences in conditions can grow over time and lead to completely different outcomes. That is why forecasts are reliable for a few hours or days, but less certain further into the future. So, sorry. Tiny difference in conditions can grow over time. So there might be a sudden high pressure winds which might blow off the clouds from a certain place. So in spite of seeing heavy rain laden clouds, you might not see the downpour of rain. So that might happen. Okay. That is why sometimes forecasts fail. Sorry. I have seen many a times We are blaming the Indian Meteorological Department for making bad forecasts, but this happens. For example, this year itself, we are experiencing a shortage in rainfall, and one of the prime factors for this happening is the air over Pacific has gone superbly warm, or maybe the El Nino effect, which is causing these changes. Otherwise, we would have had a normal monsoon. The monsoon was developing normally. However, these two have turned around the things. Okay. So generally at times weather forecasts do go wrong. Okay. Limits of scientific theories. Even the most successful theories have limits. They may fail when new conditions are explored. Measurements become more precise, but this is not a weakness. It is science's greatest strength. Scientists do not reject ideas based on opinion. So they do not form opinions. They are making proper calculations. They change them based on new evidence. So whatever new evidence has been gathered, on the basis of that, scientists make their observations. No scientific theory is ever final, and none is beyond question. This openness is what makes science trustworthy. So observation versus prediction. Versa says it will rain this afternoon because the clouds look dark. So what is the observation? Based purely on visual observation of clouds. The scientific prediction is temperature dropping? Do we see a certain drop in temperature? Do we see the winds changing? What is the wind speed direction? What was the humidity level? What is the wind directed towards? Okay, predictions are not guesses. They are reasoned expectations based on pattern based evidence. So we have certain patterns, we have observed them, and on the basis of that, we are making predictions. We are not sitting with a book and a pen, but we are making predictions. Are based on our observations in the previous patterns of a certain natural phenomena that we had observed. However, there is a possibility of these predictions going wrong. Okay. Okay. So checking viral claims on social media. Now, when you say social media, there are a lot of viral claims that are there. These days, you can post anything on social media, and if it gathers attention, it becomes viral. Because of which there is a possibility that certain phenomena which are not supposed to happen or which show no likelihood of happen are also assuming an explosive nature, and people start believing them. So a widely shared claim suggests that eating food during an eclipse is harmful. So this is a superstitious belief that eating food during an eclipse is harmful, especially in India when we know very religiously follow eclipse patterns of Surya Grahan or Chandra Grahan. So they say that if you happen to eat food during these times or even cook it, then it's going to impact on your health or it might prove harmful. However, this can be disproved by asking some scientific questions. So some scientific questions are: an eclipse is merely a phenomenon involving shadows. So either the moon is coming between the earth and the sun, because of which you are experiencing an eclipse. So that's a basically shadow thing. The moon is coming in between the sun and the earth. So you are seeing a shadow pattern of the sun because the moon coming in between. So it's an astronomical phenomena. However, what has this got to do with you eating or cooking food? So during an eclipse, there is no significant physical change, and factors such as temperature do not vary very drastically. Eclipse is a short phenomena or maybe a couple of hours, but nothing is going to change drastically on earth. Food does not spoil simply because it is left in a shadow. Yes, food might spoil because of microorganisms. Food might spoil because of certain drastic temperature changes that you might have evolved, but there is no such thing happening during an eclipse. Therefore, there is no physical, chemical, or biological basis. So, neither there is a physical nor chemical or biological basis for the claim that food becomes harmful during an eclipse. So, estimation, thinking in approximate numbers. You do not always need an exact answer. Approximate reasoning is an important scientific skill. Strategy, understand the situation, identify the key quantities, make a rough estimate, check does the answer make sense. So understanding the situation, identifying the key quantities that are involved, make a rough estimate and check whether it is making sense. How much air do you breathe in a day? For example, there is a question that has been asked, how much air do we breathe in a day? How is it that we will use mathematics to solve this? Breaths per minute at rest, about 12 to 15 minutes in a day. 60 into 24, that is how much? So breaths per minute at rest, about 12 to 15 minutes in a day. So 16 to 24. Total breaths per day, roughly 18,000 to 22,000, about 20,000 breaths. Volume per breath, it takes about 4 to 5 breaths to fill a party balloon, that is 2 liters. So each breath is equal to 0.5 liters. That's how mathematically we will consume air. We have calculated how much of air we are taking in per breath, that is 0.5 liters. Okay, so we see how mathematics as an equation is evolved in certain calculations of biology. This is basically biology. How much of air are we breathing? How much is the intake of air? So this is applying mathematics to biology. So about 10,000 liters of air per individual per day. Okay, 10,000 liters of air is actually the intake of per individual per day. Check 3 balloons into 2 liters into, so you will get 8640, reasonably close to 10,000. Okay. The goal of estimation is not to get an exact number, just check whether an answer is reasonable or impossible. So at times we go into an estimation mode. We are not very precise about things, but just to check whether it is reasonably correct or not. Okay. So the limits of prediction. So let's say we have the initial state. Weather depends constantly on changing variables. So these are variables which are constantly changing in the atmosphere or the weather. Variables of temperature, pressure and wind. Tiny differences in starting conditions compound over time. So these basically assume larger proportions. Forecasts are reliable for hours but uncertain for weeks. So we might say in the next hour it's going to rain. But at times when we are forecasting for a week or a month, we might go wrong because every instant there is a condition that is piling up in the atmosphere or the weather, and that might impact our predictions. That is one of the reasons why meteorological predictions, even by eminent scientists, at times goes wrong. Okay. No scientific theory is ever final. Scientists change ideas based on new measurements. This openness in science is great strength. So there is constant change, and this is basically an openness. For example, in this case, how much air do we breathe? So breaths per minute at rest is approximately 12 to 15. When you are not exercising, when you are not into heavy games, when you are not into gymming, when you are not into swimming and all, okay, you are just at rest. Doesn't mean that you are actually sleeping, but maybe your body is not in a very high requirement of energy when you are doing something just sitting. Okay, so the number of breaths that your body takes is approximately 12 to 15 per minute. Now calculate the base minutes in a day. How many minutes are there in a day? Obviously 1 hour will have 60 minutes, and this 60 minutes makes 1 hour. So we have 24 hours. So obviously we will have 1440 minutes in a day. Now in 1 minute you have 12 to 15 breaths. So in 1440 minutes into 15 breaths, so roughly 21,600 breaths is what you take in a day. 21,600. Now totally it's about 20,000, approximately let's say 20,000 breaths per day. Now you will say, why are we ignoring this? We are just trying to have a rough estimate because there is a difference between the breathing rates of older people, the kids, and obviously the middle aged people or the younger ones. Okay, so let's say we will take, now volume per breath is 1 by 4th of a party balloon. So volume per breath is 1 by 4th of a party balloon. You do not always need an exact answer. Appropriate, so how do we basically calculate how much of liters? So that's what we calculated, approximately 0.5 liters per person. Okay. How much rice would feed a family for a month? So for example, you have this question here wherein you have been asked how much of rice would feed a family for of four for a month. So to estimate how much rice would be needed to feed a family of four for a month, let's make some assumptions. We will consider that their calorie needs come from rice alone, let's say. And for an average individual who's staying in an urban area, the approximate requirement is 2000 to 2500 calories per day. Okay, and let's say we are assuming that all this calories is coming, or rather kilocalories, is coming from the food that he or she is consuming. First, we need to find out how many calories are in 100 grams of uncooked rice once it's cooked, and then use this information to determine the family's daily requirement. So that's how we average out things. That's how we calculate things. The goal here is not to arrive at an exact figure, but to see if the answer is reasonable. For example, 100 grams of rice for a month is clearly, obviously, too little. It will not be able to fulfill the requirements of an individual. Okay, while a few tons would be far too much. So we cannot estimate in terms of 100 grams of ice or tons of ice. This kind of estimation helps connect scientific principles every day, questions about food and resources, and demonstrates why approximate reasoning is an important skill in science. So an approximate reasoning of everything that we see around us, feel around us, or rather judge around us is what forms the basis of science and our calculations as well. Now, there are SI units, standard international units. Now, why is that we have to have a standard international system of units? So, for example, you are going to learn in higher classes, then when we talk about length, the standard unit considered is meter. When you're talking about a physical quantity of mass, the standard unit to measure mass is kg. When we are talking about time as a parameter, the standard unit to measure it is seconds. When we are talking about temperature, although till now you have studied Fahrenheit and Celsius, but the standard international unit of temperature is taken as Kelvin. And when we are talking about the amount of a substance, it is taken as mole. Okay, so there are 7 physical quantities which are there. Here, 1, 2, 3, 4, 5. We have discussed 5. There is something called as electric current. There is something called as electric current that forms the 6th, which is represented by I, and it is measured in amperes. There is something called as luminous intensity. Luminous intensity that is measured in candela. That is measured in candela. So these are the 7 physical basic quantities. Okay. So science uses a shared. So all these will have a specific unit. Length is measured in meters. Mass is measured in kg. Time is measured in seconds. Temperature is measured in Kelvin. Then we have amount of a substance measured in mole. Then we have luminous intensity measured in candela, and then we have electric current measured in amperes. Okay, so now we have to have a standard international unit. You must have heard about units like yard, foot, or maybe inches. All these are not standard international units. For example, a person staying in India might understand these terms because we were once a part of the British colonial empire, and they used to follow this foot pound system. So there is an MKS system of units, there is a foot pound system of units, and there is a SI system of units. This SI system of units has been recognized all over the world. So when I say I am measuring a particular distance as 60 meters, this would be understood and coded as the same across India, Russia, or any part of the world. Okay. So however, if I say 5 inches, it might not be understood by a certain person staying in Namibia what is inches, maybe, okay, because that's not a standard unit. So in order to solve complexities or disparities which might arise due to calculations in different scientific experiments, we actually follow a generalized version of units assigned to different physical quantities, and these are known as standard international units. Okay, so the cost of impression, standard units. The case study: a passenger plane ran out of fuel mid-flight, 15,000 liters short, forcing a dangerous emergency landing. Now this is very dangerous. Why? What was the cause? The ground crew used pounds instead of kilograms to calculate fuel density. This happened, and it's a real case study wherein the ground crew, they actually used pounds instead of kilograms to calculate fuel density. The lesson: science uses a shared system of international units, so results mean the exact same thing everywhere in the world. So that would mean the exact same thing everywhere in the world. The plane which is actually going from country to country, in one particular country, the fuel density was calculated in terms of pounds, and that resulted in a confusion and a shortage of fuel. While the pilot was still up in the air, he realized and quickly did a emergency landing, saving the passengers. But this could have proved a disaster. Okay, so what happened is that the fuel was filled, or rather calculated, in pounds per liter, wherein it should have been calculated as kilograms per liter. So it is very important that we follow a standard system of units, and this standard system of units will be aligned across the measurement of all physical quantities all across the world. Anybody staying in any part of the world would actually understand what physical quantity is expressed by what kind of unit. So threads of curiosity when I'm sorry. When we buy 1 kg of vegetables, we expect the same amount every day. This is possible because measurements are based on international standards, agreed international standards, not local opinions. So 1 kg is basically the unit of mass. And when we are buying 1 kg of vegetables every day, we have a certain idea about the amount of vegetable we are buying, cooking, or even consuming every day. Okay, and this is not just based on opinions. The government actually manufactures those weights which are used by different vendors to give you the vegetables. Now, airplane fuel miscalculation. A passenger plane ran out of fuel mid-flight because the ground crew used pounds per liter instead of kilograms per liter to calculate the fuel density. The plane was about 15,000 liters short of fuel, and that's a huge number. And the pilot realized this when he was up in the air along with the passengers. It had to make an emergency landing. Using standard international units every day prevents such dangerous errors. The speed of light is denoted by C because it comes from the Latin word celeritas, meaning speed. Scientific symbols come from history and international agreements, not just convenience. For example, the units that we use sometimes, let's say the unit used for force is Newton. It is after the name of a scientist. The unit used for current is ampere. It is after the name of a scientist, so it is in capital letters. The unit used for charge is represented as coulombs. The scientific letter capital C is used to represent it. Otherwise, we generally have meters, which is represented in small letters, kg, which is represented in small letters, liter, which is represented in small letters. Wherever you have a capital letter specification of units, that is generally named after a scientist. Okay. After grade 10, science splits up into branches. So the branches are physics, chemistry, biology, and of course maths. So we can have, so what do we study in physics? What do we study in physics? Matter, energy, forces, motion, electricity, light. These are the phenomena that we study in physics. Chemistry, substances, reactions, properties of matter, atoms, molecules. These are things that we study in chemistry. Living organisms, cells, genetics, ecosystems, etc. These are the things that we study in biology. Okay. 1 second. Energy, forces, motion, electricity, light. Chemistry deals with substances, reactions, properties of matter, atoms and molecules. Biology deals with living organisms, cells, genetics, ecosystems. And earth structure, atmosphere, climate, rocks are what we study in the study of earth. Just 1 minute here. Okay, so example, how does a mask work? A mask which was generally used in times of corona. How does this work? Solving real problems requires knowledge from several branches of science. During the COVID-19 pandemic, during the times of corona, we were essentially told to wear masks. So, physics, particle motion and electrostatic attraction. So, there is a particle motion and electrostatic attraction. When we sneeze, we generally blow out air, and that's something that can be causing, or rather the root source of infection in others when we sneeze without covering our face. Properties of polymer fibers. So the masks that we were using were based on polymers, and these are polymer fibers which will ensure that the amount of air that we are blowing out during a sneeze is not impacting others. Just 1 moment here. Modeling airflow and filtration efficiency. Science also connects naturally which technology, arts and social sciences. To fully understand the world, we need multiple ways of knowing. Science is a human activity. Science is not just facts and equations, it's a human activity shaped by curiosity, creativity, collaboration, careful questioning. It grows as people ask questions, test ideas, share results, and learn from mistakes. Science develops over time through the work of many individuals across different cultures and generations. So it's not just a country or a set of people which have contributed to the development of science. It's just the basic human sense of curiosity that has contributed to the development of science all across the world. Now, we have certain NCRT questions that we will be considering and discussing here. So, here we have a question. Suppose you ride a bicycle from your school to your home. You want to model the time it takes to go home from school. What details would you keep? What details could you ignore? Suggest why ignoring some details may actually be useful. Now, details to keep. So, you are trying to do what? Model the time it takes to go home from school. So you are using a bicycle to go to school from your home and you're trying to calculate the time. There are certain things which you have to keep as information and there are certain things which you need to ignore. Now, distance from school to home definitely is a detail that you have to keep. Average speed of cycling, number of traffic stops or signals, because that is going to impact the basic time it is taking for you to reach from your home to school using that cycle. Okay. But what you need to ignore, but what could also have certain connections to the study that you are making, color of the bicycle, it has got nothing to do with the motion. Exact route curves using straight line distances as approximation. Whether the road is slightly uphill or downhill for a simple model. So these are things which are definitely going to maybe impact your motion. But there would not be a certain thing to calculate the distance. You are just concerned about calculate the distance and the time of motion. So these are things that you have to ignore. Why ignoring details is useful? Ignoring unnecessary details makes the model simple enough to calculate quickly. If we try to include every bump on the road or every traffic signal, the model will become too complicated to be useful. So if you are going to take into consideration every small detail in a particular study, then it's going to become complicated. A simple model gives us a reasonable estimate that is good enough for most purposes. Okay, let's move on. What is the speed of light? Why is the speed of light denoted by c? We have just studied this and this is there as a question as well. So it is coming from the Latin word celeritas. Celeritas, so a lot of things or a lot of terminologies have actually evolved from Latin. The reason is because it's a dead language. There is no changes that are going to happen in this language, and that's the reason many scientific terms, in fact, the entire biology in which you have names of different genes and different genomes, all are there in Latin word itself. For example, for sodium also we say, in chemistry also we say that is Na. So Na is actually coming from the Latin version, which is natrium. Latin version is natrium, and so we say Na. Let's say for in biology, for tiger we say Tigris indris. Okay, so this is a biological name that is coming from Latin, which actually correlates to tiger. The symbol C for the speed of light does not stand for any English word. It comes from the Latin word celeritas, meaning speed or swiftness. Scientific symbols are often used or often chosen based on historical tradition and international agreement, not simply as abbreviations of the English name for the quantity. This is why many symbols in science seem unexpected. They carry the history of the language in which that concept was first formally studied. The speed of light is a fundamental physical constant defined exactly. So this is how the speed of light is defined: 299,792,458 meters per second. However, we generally take it to be 3 into 10 raised to 8 meters per second. This is generally taken as this value for calculations. Okay. Ready to go beyond airplane fuel miscalculation, which we have also discussed. This is also appearing as a question in your NCRT. A passenger aircraft ran out of fuel mid-flight due to unit mix-up. What does this tell us about the importance of standard units? So instead of calculating in terms of kilos, it calculated in terms of pounds. Okay. So this incident shows that using wrong units can have dangerous real-world consequences. The ground crew calculated fuel density in terms of pounds per liter instead of kilograms per liter, which are very few values. As a result, the plane carried far less fuel than it needed and had to make an emergency landing. Okay. Fortunately, the people were saved and the plane was saved as well. Otherwise, it could have been a disaster because of a simple miscalculation, not because of a technical failure. Okay. Standard units are not just a formality, they are essential for safety. Everyone in a system, which is pilots, ground crew, engineers, must use the same units all across the world. Because when a plane flies, it might cross across different destinations in different parts of the world. All need to be aligned in calculation of the units that are used in order to fill the fuel in the plane. Since emphasis standard units so that results and calculations mean the same thing everywhere in the world, a small error in units can compound into a huge error in the final results. So there was a passenger plane that ran out of fuel mid-flight, 15,000 liters short, forcing a dangerous emergency landing. What was the cause? The ground crew used pounds instead of kilograms to calculate the fuel density. Science uses a shared system of international units, so results means the exact same thing everywhere in the world. So this is something that we have already studied. Okay, let's move on. Why is kilogram used everywhere? Because it is a standard international unit. So when we are talking about kilogram, a simple uneducated village vendor selling vegetables will also understand it as kilogram, and a top eminent scientist in India will also understand it. Plus anybody staying at any part of the world would understand what a kg means. Okay, because that's the standard international unit accepted at every corner of the world. When we buy rice, vegetables or any goods by weight, we expect a kilogram to mean exactly the same amount whether we are in a shop in Chandigarh, a market in Mumbai or a store in any other country. This is possible because the kilogram is based on an internationally agreed standard, that is standard international unit, not a local object or a regional custom. Without such standard, the same word kilogram could mean different amounts in different places, making trade unfair and scientific comparison impossible. Standard units ensure that measurements are universal, results can be replicated anywhere in the world, and daily transactions are fair and trustworthy. The first person to have introduced weights and measurements was, of course, Napoleon Bonaparte. But in his times, the standard units were not the same across the world. Later, in a conference in Geneva, it was agreed mutually by scientists all across the world that we should indeed follow standard units of measurements in order to basically make use of the scientific inventions and discoveries that are being made at every corner of the world without much of confusion. So think of think of a prediction you and your family made recently. For example, the outcome of a cricket match. So let's say team A and B were playing, and you on one side supported A and the other part of the family supported B. What is based on evidence and reasoning or mainly on guesswork? So obviously you must have seen what has been the pattern of the team playing in a particular stadium, or maybe as a form of players. How can scientific thinking, so just predicting which team would win, how can scientific thinking improve? So our team will win today's cricket match based on guesswork. It was based on feeling hope or just supporting a favorite team. Okay. Based on evidence, it considered team's recent performance, pitch conditions, weather, and the opponent's weakness. How scientific thinking helps? Scientific thinking means looking for measurable patterns instead of opinions. So we are particularly interested about measurable patterns instead of opinions. So what are these measurable patterns? Okay. Checking win-loss records on this type of pitch. So team A and team B are playing. How have they been successful in the last couple of matches in this particular pitch, or how have they been unsuccessful? Comparing current form of players in a particular team A, what is the current form? Are they in form? Are they playing well? Have their seasons gone good? Okay. Analyzing past head-to-head results. So whenever these two teams have confronted each other, we in any other ground, what has been the results or the outcomes? This kind of reasoning gives a more reliable prediction than pure guesswork, just like weather forecasters use data rather than gut feeling. Okay, so this is data based. Okay, why do weather forecasters sometimes go wrong? So yes, we do weather forecasting based on previous patterns, and we look at a lot of factors like, let's say, humidity, the gathering of clouds, and so on and so forth. However, there are certain pressure changes that keep on happening, and it's a possibility that the weather forecasting might go wrong. For example, this year itself, at the start, maybe in January or February, the Indian Meteorological Department said and declared that we would have normal monsoons, which supposedly start by the end of May or June 1st. But unfortunately, the monsoons have been delayed by almost a month, and now they are saying that we might just receive a 40 to 50% shortage of rainfall because of the El Nino factor and other pressure patterns that have developed over the Pacific. So these are things that might happen just randomly. Okay, weather is governed by a large number of constantly changing variables. So there is temperature, there is air pressure, there is humidity, there is wind speed and direction and moisture content at different altitudes. Even tiny differences in these starting conditions can grow over time and produce completely different outcomes. This is sometimes called as butterfly effect. So there is a tiny thing that has happened, and that might, so example of butterfly effect. So let's say there is this earth and there is sea above it. There's a mild earthquake that has happened under the sea. So the waves will rise. Then the waves will rise. And by the time they reach the shore, they became a huge tsunami causing massive destruction. So this is how a tiny disturbance can create a huge butterfly effect. Okay. A small unmeasured variation early on can lead to a very different result later. Weather forecasting models use mathematical equations and real-time measurements from satellites, weather stations and balloons. However, no measurement tool is perfectly precise and no model can capture every detail of the atmosphere. So small errors in the initial data get amplified as the model turns forward. This is why we say that forecasts for the next few hours are usually quite reliable. So if we are forecasting the weather for the next few hours, they are more reliable because the pressure changes or the wind might not have a huge impact as it happens for a month down the line. Forecasts for 2 to 3 days ahead are reasonably good. They can still be accepted. Forecasts beyond a week become increasingly uncertain. As I said, at the start of this year, in the month of January, it was predicted that we would have good monsoons, but by the time of June, we realized that we are running in a super deficit of monsoon. Okay, this is not a failure of science. It is an honest acknowledgement of the limits of current models and measurements. Scientists continue to improve forecasting by collecting better data and building more powerful models. Okay. Let's move on. Threads of curiosity. Checking viral claims on social media. Is eating food harmful during an eclipse? We have discussed this question. We will again discuss this because it has come as a question in NCRT. So there is a viral claim that during eclipse you should not be consuming or maybe even cooking food. However, we have seen that it is not justifiable rationally. There is a widely shared belief, but it does not hold up to scientific questioning. An eclipse is purely an astronomical event, whether the moon is coming between the earth and the sun, or the earth is coming between the sun and the moon. It's a purely astronomical phenomena and is bound to happen as all three are revolving. In fact, to be very precise, at least two around the sun are revolving. Okay, passes through the earth and the sun, temporarily blocking sunlight. It is essential part of shadows. Okay, what physical changes occur in food during an eclipse? How can there be some physical changes that might occur? Because physical changes, if they happen to occur, they happen generally by microorganisms. They happen generally by huge temperature changes. But are these the factors which are actually getting influenced by the eclipse? None that has been measured. Does temperature change significantly enough to spoil food? No. An eclipse lasts only a few minutes and any temperature drop is minimal. Does food left in ordinary shade go bad? No. Okay. Is there any radiation during an eclipse? There is different from normal. No harmful radiation reaches food on the ground. Since no physical, chemical or biological mechanism can explain why food would become harmful during an eclipse, the claim has no scientific basis. This example shows how asking simple measurable questions, the core of scientific thinking, can help us evaluate viral claims rather than accepting them uncritically. So we have to basically ask rational and valuable questions in order to, you know, in order to basically nullify claims that might have no connection to an event that is happening. Right to go. How much rice would feed a family? So when we are making calculations, we have just seen how, so all calorie needs come from rice alone. An average adult needs about 2000 to 2500 kilocalories per day. 100 gram of uncooked rice provides approximately 350 to 360 kilocalories when cooked. Calculation. Daily rice needed per person is approximately about 570, roughly 0.6 kg per person per day. For 4 people, it is this much. For 30 days, this much, and so on and so forth. We can calculate how much of rice is needed by a particular family per day, per month. Describe one situation where an approximate answer is good enough and one where you would need an exact value. So let's say if we happen to discuss this, a situation where approximate answer is enough, estimating how much rice is needed for a family of 4 a month, you need not calculate down the last gram. Okay, so you just have to have a fair idea about the calorie requirement and how much of dependency on rice is there to fulfill the calorie requirement per individual in that particular family. A rough estimate of a few kilograms is perfectly helpful for planning grocery shopping. Situation where exact value is needed, calculating the amount of fuel required for an airplane before a long flight. Now airplanes, we cannot have anything which can go wrong. So when we are planning a flight, we need to have an exact, so even a small error in the calculation of units can actually lead to fuel running out mid-flight, which is extremely dangerous. Hence, we are supposed to have a precise detailing about this. Sorry. Now choose real life object, maybe pressure cooker or a mobile phone, or a problem, maybe traffic jam near your school. List what kind of ideas from physics, chemistry, biology, earth science or mathematics are involved. Show at least two branches of science which connect with your example. So let's say you have chosen uh, mobile phones. You have chosen basically mobile phones. So physics. Electricity powers the phone, light from the screen, radio waves transmit signals, electromagnetic induction charges the battery. So this is where physics is concerned. So electricity powers the phone, we all charge the phone from the screen, radio waves transmit signals. Radio waves are the ones which transmit signals when you're calling or sending a message to anyone. These are basically your radio waves. Electromagnetic induction charges the battery. When you actually charge the battery, how is it happening? Battery stores and releases energy through chemical reactions. So the phone which is there, which has a battery, is actually supplying the power needed when you are using the phone. Skin made of special compounds. Now biology, the phone's design considers how humans hold it. So if you have a phone, you cannot have a flat phone like a tab. You have to use it so that you can comfortably carry it in your hands. Okay. So that is called agronomics, which is a part of biology. Screen brightness, so that it is not harmful to your eyes, is adjusted for human eye safety. Okay, so these are things that these are the biological factors that you need to take into consideration. Mathematics, algorithms process data. Encryption protects messages. So you have WhatsApp encryption, you have Facebook encryption, and so on and so forth, the different social media sites that you have. So it protects messages. Compression reduces photo video file size. So you can have a good amount of storage provided you use compression. So these are mathematical algorithms. So just in a simple use of a phone, you see how science is embedded and compiled. So the branches, physics. So when you basically see a cell phone, okay. So there are electromagnetic induction charges the battery, radio waves, they transmit the signals. In chemistry, the battery stores and releases energy through chemical reactions. Math, encryption protects messages, algorithms compress photos, and screen brightness algorithms are calibrated for human safety. The natural world has no divisions. Real world problems require multiple ways of knowing. So we might use all the branches of science in designing a particular equipment. Okay. So physics perspective, let's say if we are talking about an eclipse, the eclipse is just the moon blocking the sun's light. Chemistry perspective, Earth's atmosphere does not change chemical composition during a shadow. So there is not a sudden change. Okay, temperatures might drop by a fraction, but not much. Biological perspective, no biological mechanisms exist for a shadow to poison food. So this concept is not agreeable to science. Okay, whether this is true or not, at least rationally it cannot be explained by science if we are considering physics, chemistry, or biology. So asking simple measurable questions helps evaluate viral claims instead of accepting them with certainty. Okay, so these are the things that we have. Two branches. So physics and chemistry. Physics and chemistry are most directly connected. The battery uses chemical reactions to produce electrical energy, and the screen uses both electrical signals and chemical materials to display images. So a mask works by blocking tiny particles like virus droplets from entering or leaving during the nose to the mouth. So understanding this involves physics, obviously. So particles in air are constantly moving. Masks use electrostatic attraction. The fibers in the mask carry charge that attracts and traps the tiny particles, even the ones that are of pore size. So in these masks, there is a electrostatic attraction. Okay. The fibers are made of polymers like polypropylene. The chemical structure of these polymers make them good at generating and holding static charge. Virus like SARS-CoV-2 travel in tiny droplets. Their size, that is zero point 0.1 microns, determines what kind of filtration is needed to block them. Now, what is mathematics? Engineers model airflow and filtration efficiency, calculating what percentage of particles are blocked at different breathing speeds. So, a just 10 rupees mask has so much of science involved, so much of science involved in order to manufacture and so that everybody can make use of it. So, a simple looking mask is actually a product of knowledge from physics, chemistry, biology, and mathematics working together. One second. Oh, oh, sorry. So just designing a simple mask has so much of science involved in it. A 10 rupees mask which you can easily get. Okay. So science is not just equations. Science is not just equations and is isolated facts. It grows as people across cultures and generations ask questions, test ideas, share results, and learn from mistakes. So this is concerned with curiosity, collaboration, creativity, careful questioning. Science is the shared story of how we figure out the world. So this is a shared story of how we figure out the world. So that basically covers this chapter. Any questions, please do let me know. Thank you so much for your valuable time.